Now that we've talked about sampling distributions, let's talk about the central limit theorem. So our central limit theorem actually says a few things about a sampling distribution. Let's suppose we know our population mean is mu and our standard deviation is sigma. We also know that we have a sampling distribution of size n, so we've looked at a lot of different samples, all of size n. So the central limit theorem actually tells us three things. The first thing the central limit theorem tells us is that the sampling distribution is normally distributed. This is something that we had looked at in our previous video when we talked about sampling distributions. We found a sampling distribution, drew the histogram, and showed that it was normal. And this will actually always be true. Our sampling distribution will be normally distributed. The second thing it tells us is the mean of the sampling distribution is mu. So what that means is if we actually know the population standard deviation and we look at the sampling distribution, we have a bunch of means, and if we find the average of all of those means, it will be the same as the population mean. The last thing it tells us is about the standard deviation. The standard deviation of the sampling distribution is the population standard distribution divided by the square root of n. So it's the sample size over the square root of n. So let's look into this a little bit more and see exactly what it is that we're saying. Here's the sampling distribution we built earlier for these quiz grades 2, 6, 4, and 8. So the 2, 6, 4, and 8, that is our entire population, so we can easily find the mean and standard deviation of that. And if we do that, we get that mu is 5 and sigma is 2.236. So I actually found both the mean and standard deviation of just those four numbers, 2, 6, 4, and 8. After that, we broke it down into these samples of size 2 and find the mean of each of these samples. So now I want to take the mean of all of those means. And if we do that, we get the mean is 5. So if we actually average up all of these means, we do get a mean of 5, which is the exact same as the population mean. So that was the second piece of the central limit theorem. If I find the standard deviation of all of those means, I get that it's 1.581, which is the same as the population standard deviation, 2.236, divided by the square root of 2, the square root of the sample size. And that's what the central limit theorem was saying in the third part. The first part was that it is normally distributed, which we saw when we built the histogram for this. And so the central limit theorem says that's always going to be the case. It'll be normally distributed. My mean will be the same as the population mean, and my standard deviation is the population standard deviation divided by the square root of the sample size. For my previous example, when I looked at it, the mean and standard deviation actually worked out to be exactly what the central limit theorem said, and the histogram was exactly normal. In reality, that's not going to be the case. This worked out because I actually did take every single possible sample of size 2, but most of the time it's not going to be possible to take every single possible sample. So instead, this is really just an approximation. It's approximately normal. The sample means are going to be approximately the population mean, and the standard deviation will be approximately standard deviation divided by the square root of n. And the bigger the sample size, the better the approximation will be. However, we do have a couple of caveats here on when we can actually use this. If our original variable was originally normally distributed, then the central limit theorem will apply no matter what. So if we started with something that was normally distributed and we did this sampling distribution, it will still be normally distributed. If we didn't start with something normally distributed, then we need a sample size of larger than 30. Then our central limit theorem will work. And like I said before, if you use a bigger sample, it will be a better approximation, but we do need at least 30. So let's actually look at some examples of how we actually use this. Here's an example of a central limit theorem question. Children watch an average of 25 hours of TV per week with standard deviation of 3 hours. We're going to assume this is normally distributed, and we're going to select 20 children. What's the probability they watch an average of more than 26 hours per week? So we're not looking at the total sum, the number that these 20 children watch. We're looking at, on average, how much do these 20 children watch? And this is going to be very, very similar to a normal distribution problem. We have that our mean is 25. 26 is somewhere to the right. And we want to know the chance they watch more. When dealing with normal distribution problems, we need to use the normal command on our calculator. Since we want area to the right, we need to do 1 minus normal. The first number we enter on the calculator is the mean, and the central limit theorem says the mean doesn't change, it's still 25. The second number we need to enter is the standard deviation, and the central limit theorem says the standard deviation does change. It's the original standard deviation divided by the square root of the sample size. So our original standard deviation was 3, and our sample size is 20 since we have 20 children. We then have the number that we're looking for in particular, in this case 26. Now that we have that, we can type that into our calculator. So here's our calculator. I'm going to click the 3 dots at the top right of the keyboard, and I'm going to search for normal since we need the normal command. The mean was 25. Our standard deviation was 3 divided by square root of 20. And the value we're looking for was 26. Now we actually didn't want this. We wanted 1 minus that, so I'll add the 1 minus at the front. And we get 0.068, or 6.8%. So there's a 6.8% chance these 20 children watch an average of more than 26 hours of TV per week. Let's look at another example. The average age of a vehicle in the US is 96 months, with standard deviation of 16 months. We're going to select 36 cars at random, and we want to know what's the chance that the mean age is between 90 and 100 months. So we don't necessarily say this one's normally distributed, but our sample size is bigger than 30, so our central limit theorem says we can use normal. We know the mean is 96, and we want to know the chance it's between 90 and 100. When I'm given 2 values and I'm looking for between, we need to subtract the biggest minus the smallest. So we're going to start with normal of the mean, which is 96. The standard deviation, which is the original standard deviation divided by the square root of the sample size, so 16 over square root of 36. And then we need our value, and for this we need the bigger of the 2 values, 100. We're then going to subtract the lower value. So our mean and standard deviation is still the same. The only thing that changes is our value changes from 100 to 90. So now we just need to type this into our calculator. I'm going to click the 3 dots, select normal. We had a mean of 96. Standard deviation was 16 divided by the square root of 36. And the first value was 100. We then subtracted. I'll go back into my menu and select normal again. The mean is still 96. Standard deviation is still 16 divided by the square root of 36. And this time my value is 90. So we get about 92. So we have about 0.92 or 92% chance that the mean age is between 90 and 100 months.